Okay, let's start. Okay, last lecture, we finished dynamics for single rigid body. This lecture, lecture 9, we're primarily focused on dynamics of open chains, basically robot dynamics. I think many of you have learned robot dynamics in their introductory robotic class, and maybe you have learned how to derive them. I'm not sure how much you remember, but today we're going to derive the dynamics of open chain from scratch. Okay, and the only thing I require you to remember for now is the single rigid body dynamics concepts and some key properties. Let me briefly recall what the key kind of properties or definitions I need you to know for single rigid body dynamics. First of all, I think the most important concept we introduced is called spatial acceleration. Okay, we denote as script A. It's a little bit bad notation, but let's call it script A. That means the spatial acceleration is in R6. Okay, and then by definition, for example, what's the definition of this spatial velocity, spatial acceleration? Let's say a rigid body, spatial acceleration, by definition is what?
Is the derivative of the spatial velocity.
The derivative of that, okay? Here's a coordinate free. This is a coordinate free. I didn't say which coordinate I want to take to represent this velocity, but anyway, this is a vector, is a motion vector. Okay, it's a 6-dimensional motion vector. And if I take derivative, I got another 6-dimensional vector, and that vector is called acceleration of the body. Okay, and then I start to work with different coordinate. Oftentimes, the most I would say inertia to work. Let's say working with inertia frame, or stationary frame. That reference frame that does not move on its own, then the entire motion is because the body is moving with respect to that particular reference frame. So in this case, a body dot O, that is that means take derivative and express that derivative in O is nothing but the apparent derivative, right? This is hold on. This is the body in O's coordinate, and you take derivative, okay? Which we call this, oftentimes we call this V body circle. Here is O, right? Or this is apparent derivative. Just take derivative with respect to the coordinate numbers. Yes.
Is there a typo in a body? There's a point on the top of the
Oh, there's no point anymore. Sorry. You're right. Great. Yeah, you should correct me. I'll have a lot of typos in the video. That's good. Well, keep reminding me. And if let's say working with moving frame, okay, that's where the special cross product arise, or the so-called Lie bracket shows up, right? So that's the somehow a challenging part. We spent quite some effort to explain why that's the case. And for now, definitely you can read, kind of watch our previous video. In this case, the acceleration expressed in B, okay, you can take derivative by working with B, and it's d dt, the apparent derivative, that the body's velocity coordinate in B. Okay, if that coordinate is changing over time, of course you have acceleration, but also if the coordinate of the body in B does not change, but the B is changing, well, then we will have other terms, right? So that will be the velocity of B also contribute to new kind of motion, and the cross. This is a spatial cross product. This is V body B. Okay, that's the rigid body. This is the frame B's velocity. Okay, and overall we know, well, this guy is a VB B cross. This is 6x6 matrix, right? 6x6 matrix. Okay, that's a sorry, this, well, the matrix representation of that spatial cross product. Okay, and we also know the change of coordinate. Change of coordinate for this is the same as a change of coordinate for velocity twist. So if I want to say this is OB, then I can use this acceleration, which is body in O. If you change coordinate, this is nothing but adjoint operator, right, for the frame pose. But this is the change of coordinate for acceleration the same way. And then we also got some interesting fact. One is almost like a review. It's R dot equal to omega A cross RA. The orientation of A derivative equals omega of the A frame. This is the instantaneous velocity of that frame, okay? And cross the current orientation of A. And we proved that in lecture 5, I think, when we talk about instantaneous velocity, and the R times omega gave me another 3/1 vector. If it takes skew symmetric, I can do that. But I can do the skew symmetric first, then pre and the post multiply by R and R transpose. Okay, in analogy, what we have is here, it's, let me make it bigger. Sorry. What is it? Go. Okay. Why I have this? Anyway, this is XA. Let's use a reference frame to talk about this. This is change of coordinate for twist or acceleration, they're the same. Or it is a joint of TAO, right? And this take derivative. If you take derivative of this, this gives you V of A cross omega, XAO, right? These two are exactly the same. This is a rotational version of it. This is the twist version of it. Okay, and when we write like this, the RA is not an operator. Okay, it represents the pose of A. In particular here, XA, although I constantly tell you this is the change of coordinate for twist because that's easy to picture, right? And this is actually its column of XA in O is actually the motion basis vectors express the elementary motion with respect to the coordinate frame A, right? And the first column is the rotation, unit speed rotation about OX axis. Okay, it has physical quantities. And if that A is moving, that motion's description also changes. And that change captured by this spatial cross product. Of course, it has a matrix form to distinguish from R3 skew symmetric. I use a cross here just to make sure this is 6x6 matrix. Sorry, times XAO. That's it. And also similar to the other one, I also have, let's say, for general adjoint operator, this times twist. This gives me another 6x6 matrix, vector twist. If I do this matrix representation, and I will have X, I can do the matrix representation first, then do it back. Okay, we didn't prove it. I think I need to have you prove it during homeworks, most algebraic manipulations. And you can check this is the property, and you can think about this property the same as the one we saw before. Okay, then we start talking about something like a range, right? Let's say spatial range, a spatial force, which will be range. And we know range consists of two parts, and you can represent in different frames. And the first part is the moment about, if you pick a frame, it's a moment about that origin of that frame, and you represent that thing about in the same frame. And it has a linear component with its FB. We also know that force also can do a change of coordinate, which will have FA equal to FXBA star. It's a different change of coordinate. Star and FB, I think we derive it. And also you know that FBA star equal to XAB transpose. Okay, I think we already derived everything here. And whenever you do force spatial cross product, let's say if you want to know, let's just introduce the spatial cross product for force. And in this way here, this guy, let's say XBA, let me use A0 inertia frame, okay? Let's say A0 dot, let's say this star will equal to the spatial cross product A frames spatial velocity cross. That cross is different from the spatial cross before. It has a little bit difference. So it has a star there and the times, that's using matrix repetition, times XAO star. Okay, and we have formula for both of them. That's the spatial force. Overall, also we know joint torque. Okay, joint torque. If you have a, let's say you have a joint, and the joint will provide force, right? The wrench, okay, in general, but not all the wrench contribute to the motion, because some of them is really kind of reaction force to counteract the structure force. Okay, so only certain direction you can move, and you just torque times the motion. If the direction of motion is clear, equal to the you can think about velocity times, that's a power, right? Velocity transpose F, that's a power. Okay, and the velocity we know is S theta dot, right? That's our velocity. So overall, we'll say torque is nothing but, no, sorry, this is transpose F, or F transpose S, either way is fine. It's just projecting your 60-meter range on the screw axis, you get the torque. Okay, so that's what we introduced. And we also introduced some kind of simple stuff, which is spatial momentum. I spent quite some time on explaining this. Spatial momentum is h of a, have two components. This is the phi of a, let's call it OA, sorry. It is angular momentum about the origin of the reference frame, and the linear momentum part has nothing to do with the reference point. And also we know A equal to the same way like force transpose, change of coordinate. And this is B, right? And then we have a spatial inertia matrix, which becomes 6 by 6, which is I 6 by 6. Let's say typically we'll do that with a frame fixed to the body. Suppose the central mass of the body, then it becomes diagonal. So it's a bar in C, that's diagonal, 0, 0. And this is I'm 3 by 3 identity matrix, right? If you want to represent it in other frame, no matter what that frame is, as long as you know the rigid body transformation part, you can do this A C to A star I times, this is C, and from A to C, right? So the inertia matrix really maps from the motion space, maps from the twist to a force lag property from the force space. That's why the change of coordinate before and after is you're using the corresponding change of coordinate formula. Okay. Next one is this, right? We introduce single rigid body, Newton-Euler equations. And this one is very simple, right? This guy is due to the speed is changing. You have acceleration. That's one effect due to the force. And the other effect, this guy is due to the inertia is also changing over time. So overall, I have this two terms. And this is a coordinate free, right? This is a coordinate free. I think everyone should remember this one, coordinate free. And that means I can use whatever coordinate to express this form, and the formula are exactly the same. You don't change formulas. You don't change formula adding different terms because of a less convenient coordinate system has been chosen. You just use the same formula. Okay, works for all. All right, so that's for single rigid bodies, spatial acceleration, spatial range, spatial force, momentum and inertia, and also the Newton-Euler equation for single rigid body. Okay, the robot, as I mentioned before, they consist of, in this class, okay, it consists of multiple rigid links or bodies. Sometimes I use them interchangeably. Rigid bodies connected through, interconnected through joints. So that's a robot in this class. Of course, it's not the very general definition. A lot of people study soft robotics nowadays. So this guy we only consider each link is a rigid body. All right. So you may think, okay, I have, for example, I have three body. Okay, they are connected. 1, 2, 3. Then this guy, if you look at this guy separately, let's not put it into the system. This guy separately, they will have, let's say this is my gravity, and there's a force that applied from 1 to 2. I will call that F2. This is this guy. And there's a force from F2 to F3. That's a force he applied to the next body. Let's call that, he also applied to other things, so that let's call that F, this is F2, this is called F3. All right, if you look at this figure, you can immediately write down the single rigid body dynamics using this guy, right? So this guy's motion is completely characterized by what? By external forces, and of course including gravity. But you have a chain of robots, you have a chain of different bodies, and their restrictions are sometimes a little bit more involved. And what we are trying to do is that we're trying to have a systematic way to derive the entire body of motion, but not only in terms of looking at separate its body individually, okay, separately. We hope we can derive this dynamic equation in the joint space, because all the motion and the force are provided by the joint. Okay, so overall, what we're looking for today, we are going to derive this guy. Okay, this is can be rather general, because sometimes you will see c theta dot, the Coriolis term, times tau of g times j transpose f external, times whatever things that may make sense in your particular application. Okay, I don't want to derive every single cases, but let's derive one case so that you know how to apply or how to deal with more general case. Okay, let me ask, maybe Daifeng earlier. Maybe Bowen earlier.
Oh, yeah.
Okay. So have you learned about this?
No.
Dynamics of the equation? No?
Yeah.
You have learned or not? You didn't know?
I don't learn this.
Oh, okay. All right. Have you seen this before?
I don't see this.
You don't see that. Okay, you are completely a kinematics guy then. Okay, good. What about Liu Ben? Liu Ben is there?
Yeah, I learned it in the in that book, in the mathematical introduction to robotics.
Okay, then this is a review for you then. Okay, all right. Okay, so this one is pretty popular. Even I think most introductory. Su Yinghan is there. I think he may have taken this class before. Yinghan, can you speak? I saw your name. Yinghan.
Zhang 老师, my microphone is working now.
Oh, okay. Definitely. Did you learn this in your undergraduate robotic class?
Yes, but not very deep, or like just a little about this formula. Like we learned
Did you derive it from?
Newton-Euler.
Okay.
No, we didn't. We just know this kind of a form of this formula. Yeah.
Okay. All right, got you. All right, then I see that's maybe most people, some people didn't say it. Some people have learned it a little bit before without derivations. Today we are going to derive everything. Hopefully that's. I think you all have the tools to truly understand how this one can be derived, right? I'm not going to explain too much about this formula. It will be clear after we derive them. I just want to introduce two keywords that we're going to use or refer to oftentimes in this class, and you may also see this in other place. So key thing I want to emphasize, one is called, when you talk about dynamics, okay, especially in robot systems, one is called forward dynamics. Now, this is almost like for example, a simulation. What do I mean by forward dynamics? Everything is working forward in time. It's a causal behavior. Okay, so if you give me a force or torque, I can tell you motion. Okay, I can tell you exactly the motion. That's kind of a forward dynamics, because the motion is generated by force. So for dynamics in the particular setup of robotic system is basically determine acceleration theta double dot acceleration. Okay, and given the current system state, which is theta and theta dot, you know theta and theta dot, and these are still kinematics level, right? Only acceleration are related to force and torque according to Newton's law. Okay, so and determine the acceleration and the joint force given the state and the joint force and torques, maybe some external force as well. Okay, given force, compute acceleration, forward dynamics. Inverse dynamics is very useful for robotic systems because we want to design what are good input or torque input to send to each joint. Okay, so that's called inverse dynamics. You tell me your desired motion. Let me write it down. So given desired motion, maybe in terms of theta dot, theta double dot. Okay, motion is those joint variables time derivatives, and it's a signal of the trajectory of the joints, right? And I want to find the required torque. Okay, to generate this motion, to generate the desired motion. If you want a particular path and you want some kind of torque, you want to find out what torque can generate that motion, right? That's inverse dynamics. It turns out numerically, this one is easier, conceptually easier. Inverse dynamics is more like a fundamental building block to almost everything. Including the forward dynamics, oftentimes you need to call inverse dynamics subroutine to compute the forward dynamics. Okay, we'll see how it works out. Right. In deriving this, I think most people learned before. There are two ways, by the way. There's a Lagrangian approach. There's a Newton-Euler recursive approach. Roughly speaking, there's drawbacks, advantages of each part, but most of the numerical software, they will use Newton-Euler recursive type of formulation. They have different variations, maybe, and it's often used to for numerical solutions. Yes, so the Newton-Euler approach, I think, is more. I think it's less. is completely undervalued. I don't think our undergrad class teach too much about these recursive Newton-Euler algorithms. And this part is more elegant. You can derive formulas for simple robots, and you can analyze its properties. And this one is more algorithmic. You know exactly the logic flow, how the robot dynamics, how the robot motion is generated. To me, I like this one maybe 10 times better than the other one, because it helps me understand what's going on. If you see the code, you see what are the logical steps, because if a computer can understand something, that means it's already kind of broken into very, very easy to follow building blocks. And that building blocks actually work with each other in a very logical way. Otherwise, computer wouldn't do it, right? So I think, so that's why we focus on Newton-Euler formulation. We primarily follow Featherstone, Spock, okay, and also I somehow adopt note on this part quite a bit, Pat Vincing's note on this part. He has very brilliant class on optimization-based robotics. I kind of benefit quite a bit from his note. All right, let's start. It's actually not hard. Let's directly start this derivation. Suppose we have a 4-body system, 1, 2, 3, 4. How did we number the body? We just the first body, first link, second link. And there's a tricky part is that it's a tree. Its link may have multiple descendants, let's call that children, but they only have one parent. Okay, that's a tree. So in this case, I would say this is my I, means as body or as joint. Okay, the joint I connects from its parent of I to I. For example, in this case, this guy, this is body I, the parent I is 0, right? So let me explain the parent first, okay? So for parent I, for example, let's say parent Liu Ben. I'm going to ask you, what's the parent of 3?
Parent of 3 is link 2.
It's 2, okay? And the parent of 4
is link 2.
Yeah, one parent can have 2 children, right?
Yeah.
And the one children cannot have 2 parents. Okay. Anyway, that's the analogy. But for children part, I say, let's say children C of 2, it would be just 2 children, right? It has 3, it also has 4. And if I want to, the other case, for example, I would say the children of 1 is it's just 2, right? It's just 1 children. Okay, that's the notation, all right. Maybe I ask Fuzen now. So joint I connect parent I to I. So what do you think? This is joint what? The red arrow I draw here, you think it is joint 1 or 2 or 0?
This is joint 0.
Joint 0 would connect parent 0 to joint to body I, to body 0.
1. Sorry.
So this is joint what?
This is joint 1.
Yes, that's the convention. We are trying to make sure we are on the same stage, okay? This will be my joint 2. Let's connect parent of 2 to body 2. So, okay, that's good. And we attach a frame to, let's see, attach frame to body I at the joint, okay? Typically at the joint. For example, I would say, I may say this is my joint, let's call it X4 head, Y4 head. Z will be pointing outside outward, pointing out of the paper, then this is my local coordinate 4. Okay, so the frame 4, let me see, frame adjoint. For example, I may ask for the frame 4 moves. Does it move with the frame 4, body 4 or not?
It's not moved with the body 4. It's
okay.
Body 2.
Move with body 2. Of course, body 2 moves and body 4 also move, right? Frame 4 moves with body 4, by the way. That's what I mean by attached to the body. So body moves, frame moves. If you think about body 4 is rotating, the frame also rotates. It's a local or body frame. Okay, and its center of origin is located at the joint 4. Then that's clear now?
Yes.
Whenever body 4 moves, you're right. Okay, when body 2 moves, frame 4 also move. That frame 4 move not because of body 2 move or not. It's because of body 4 is moving with body 2. Okay, it's body 4 is the only thing matters here, right? Now, I would say spatial velocity is the screw axis of its joint. It's quite important. We will denote this SI as the screw joint of joint I. For example, I may say S4, maybe for them again. S4 in local coordinate. What is it? Suppose, well, yeah, I think that's clear. Yeah. What is
it should be 0, 0, 1, 0, 0, 0.
Does this change with body force velocities or positions?
No.
It's a local coordinate, okay? You can think about it, no matter how where the body 4 is in the space, you always have the same coordinate for screw axis 4. It's a constant. This is a constant. Okay, in local coordinate, this is a constant. That's by default, all my vector here is expressed in local frame. Okay, so if I move from body to body, I want to add things up, I need to change coordinate. Okay, but for now, for this is the most convenient setup. And so spatial velocity, a spatial acceleration is of each body is this. For example, well, that's what we are trying to compute. Okay, and here is the guy is from Fi. I didn't say from where to where. It's force, actually our range. This is 60. Okay, all the special force onto body I from body parent I. So if I say this is my body 2, the joint of the parent, this joint 2, this will be my, hold on, this is my F2. Okay, it's the force from parent of 2, that means 1 to 2. Okay, so that's the force. Okay, with that, let's directly cover the recursive Newton-Euler algorithm. Okay, so first, and they have 2 paths, forward path and backward path. That's how the algorithm is defined, but the theory-wise, it's not hard. Let's just do it from scratch. Okay. So this step is actually the forward path is that typically I already look at this, right? Just think about the inverse dynamics. Let's say we want to compute tau, right? Recall our inverse dynamics. We want to compute tau, inverse dynamics with you given theta dot, and what else? Maybe external force, something like that. What is it? Oh, theta double dot. Also theta double dot, of course, given the acceleration, you want to find the desired torque. Okay, so far we don't know anything. If you know this equation, of course, you can find it. You plug in, you find torque, but we are trying to derive this equation, right? And especially how these terms relate to different things about the rigid body or about the robot, with M matrix and the Coriolis term, how do they relate to the robot properties? That's what we are looking for. Okay, so first of all, I need to, the forward path part is just given this, I want to find each individual body's spatial velocity and spatial acceleration. Basically, I want to find the motion of its body. Now, what's given is what? It's given, this is given motion of joint variables, okay? I want to use them to propagate to find out the motion of each body. Okay, they are different or slightly different. Joint only describe motion of, let's say, joint, this joint only describe relative motion of 2 with respect to 1. Okay, this is a local relative motion descriptor. Okay, we are looking for all this combined effect on each of the body. All right, so that's our goal. Okay, let's say this is quite simple actually. Let's do that by simple kind of recursive way. Let's start from simple ones. So velocity. Let's say v of 1. We know we are given all the theta, theta dot, theta double dot. Okay, let's not number about the external force. Let's think they are 0. Maybe Liuben, what is the v of 1? If you want to express them using our notation before and also the given theta variables, what is the theta of v1?
V1 is just V1, the origin at the 0 position.
Well, yeah, v1 is the velocity of body 1. Okay, this is my v1. And how does v1 relate to all the joint variables? Velocities. So let's say v1 means body 1 is moving, right? Body 1 is moving. That motion is due to what? Due to which joint?
Zeta 1.
The joint 1, right?
Yeah.
Joint 1. So v1 is nothing but s1 theta 1 dot.
Yeah.
Okay, square axis times the how fast you rotate about that square axis. That gave you the rigid body velocity of body 1. Okay, that's, well, here is a coordinate free. Then if we continue coordinate free, let's say v2 would be v1 plus v2 relative to v1. Okay, the v1's motion, that's the background. Okay, and then v2 relative to v1 also have a relative speed, and we did this in the Jacobian case. This is v1. Let's use square axis. Maybe I ask Fuzhen now. I think last time he was confused. This part. What is it, Fuzhen?
This should equal to S1 set 1 dot S2 set 2 dot.
You're not confident? Sounds you're not, you're still okay or not? What do you think?
Yes, this should be right.
This is correct. It's very simple. All right. V2's velocity is just V1's velocity plus V2 relative to V1's velocity. That's it. And it is a coordinate-free representation. If I want to do coordinate, I will do something different, because let's work with local coordinate, because as I mentioned, all the coordinate, depending on which quantity you're talking about, the coordinate we use is the local coordinate, local to that body, right? So local coordinate, what we have is let's say v1 is v1 is fine, right? V1 in 1 is is1 in 1 theta 1 dot. Okay, that's the beginning of the loop. Let's say the most important, the v2. V2, of course, in 2 is what? V1 plus this, right? Is this plus this? But I want to express in 2 frame 2, right? So that will be because is1 will represent it in local coordinate. That's our convention. So then I need to do a change of coordinate from 1 to 2 times theta 1 dot plus this is x2 will be s2 in 2, right? So I don't need to change. Then theta 2 dot. Okay, so in general, I will have in general. So vi, of course, in I equals to the previous one, the parent vi, right? Parent vpi into sorry. The parent VPI expressed in PI, and they do a change coordinate from the parent frame to my current frame I, and plus I theta I dot. So the algorithm just proceeds recursively, right? So at time, sometime it will be you got VI. Next time you find VI plus 1, and you just do a change coordinate to get the previous link's velocity and then plus the relative velocity of the current link with respect to the previous link, right? So that's our formula. I think that's I summarized here. Okay, but that's the acceleration. That's the kinematics level. What we truly care about is really the dynamics part. In dynamics, I think we should be very kind of we should be able to do it. May confuse someone. For acceleration level, let's direct work on 2. Okay, let's think we already have acceleration for 1. The 2 part will be a2. Okay, a2 acceleration. A2 is what? It's v2 dot. If you use coordinate for it, it's v2 dot, and we know v2 dot is, let's say, v1 plus v2 relative 1. That's what we use, right? So you take dot, you take dot. Overall, you have this is a1. This dot is a1 plus this is a2 relative 1. Okay, which is just this take dot, right? This is cannot be used for computation, but conceptually, what we're doing is this. And in coordinate, we use working with local coordinate, right? A22 would equal to x1 2, because you know a1, right? A1 in 1. That's my first term. The second term is this, right? Is you take derivative and then express that derivative in the new coordinate frame. So basically, if you do my notation, this d and the dt, this relative motion was described by is2, right? Theta dot, and they express this in 2. Here, this part is my coordinate free notation. The derivative of this is a twist, right? This twist represented by the square axis as 2. And I want to take derivative with respect to that. So then I think I need more space. Hold on. Over here. Okay, then I need to find out what this one is, right? So that one is, let's say d dt s2 theta 2, sorry, this is the 2 dot expression 2 equals to, I may ask Liuben maybe, what is it? Is first of all a apparent derivative first, right? So it's d dt s2 into theta 2 dot take derivative. Agree? So this is my v2. So here is my v2 in 2. This is a derivative of the coordinate. This is a parent derivative. Leuven earlier.
Yeah.
This part okay? And what else?
Yeah. Plus d theta double dot plus s2 to 2.
Well, that's this term, right? That's this term.
Yeah.
What? Let's not worry about this term. So that's the apparent derivative of v22 because we're taking derivative of v2, right? Yeah. And we use frame 2. Frame 2 is moving or not?
Frame 2 is moving.
Yeah, frame 2 is moving. What's frame 2's velocity?
The frame 2's velocity equal v1 plus v2.
Will be just okay. Yes, of course, it will be just the v2, right? Frame 2 is attached to body 2, so body 2's velocity will be frame 2's velocity.
Yeah.
They are rigid body. So frame 2 has a velocity. Let's use 2 to represent it. Then you need to cross, because apparent derivative and all this guy is that frame 2 is moving, and frame 2's velocity cross s2 to theta 2 dot. Okay. If you do this, take derivative inside. Because s2, I think I asked Fujin already that this is a constant, right? So that if you take derivative there, the apparent derivative part is only theta 2 double dot plus v2 to cross theta 2 to theta 2 dot. Okay, that will be my that will be this term. Overall, we will have a22 equal x1 to a11 plus plus v2 to cross the spatial cross product s2 to theta 2 dot plus s2 to theta 2 double dot. Okay, that's maybe our first non-essential use. Well, we use that before a spatial cross product because coordinate free is very easy. If you work with coordinate, you have to take account of the frame maybe moving. In this case, the frame is moving, right? The frame is moving because frame 1 is also moving as well. So that's the case. And overall, we have, let me not write everything. Overall, we'll have this formula, okay? Acceleration of that is the previous link acceleration. You change coordinate to the current frame, plus the frame's velocity, the reference frame's velocity cross that this vector expressed in the local frame I, and plus the screw axis of I times theta I double dot. That's exactly what we have in these three terms. Okay, I hope you're okay with it. Okay, let's continue the discussion. The forward path is just involve these two formulas. This one is propagate the velocity of its body, and the other one is propagate the acceleration of its body. The acceleration has some non-tricky part that I think the spatial algebra make it much simpler already, but it still may take you some effort to truly understand it. What we're essentially doing is that given the motion of joints, we already computed the motion of its body. The motion includes velocity and acceleration. Okay, and now we can use those motion, acceleration to compute the forces, because its body is a single rigid body. We can use just Newton-Euler equation to find out what are the force that are really kind of can be used to generate this motion. Okay. So this part, I think, I may not follow that formula. Let's use some kind of a example. Okay, let's say for body, let's say for body four here, it has actually it has no kind of does not have any children anymore. It has an own parent. If you just look at body 4 as standalone rigid body, we just use Newton-Euler equation. We can say F4. This is a force from this is F4, right? This is F4, and this force provided from link 2 to body 4. Okay, and also it has a gravity. Let's call that the gravity is this may be, hold on, this may be my gravity. Let's use spatial range. That will be G of 4 gravity. Let's say that's my gravity force. So I would say that's the 2 force applied to the body, right? So this plus, let's say Fg of 4 equal to the motion, right? This is total net wrench equals to, according to Newton-Euler, this is I4 A4 plus V4 cross I4 V4. Okay, that's it. Right? That's it. That's the Newton-Euler equation. That's why we need V4. We need A4 because that's how we can find. So these things are given already, right? So overall, I4 equal to I4 A4 plus V4 cross I4 V4 minus FG4. Okay, the gravity, because everything here, everything on this side is known. Okay, this guy is known. The inertial property you have to know of the inertial matrix. Velocity we already computed, acceleration computed, and this is a force, gravity force. Okay, and that's can be computed easily. Note, typically we'll write like that. So this is let's say Fg4 is inertia of G times Ag in 4. Okay, that's acceleration of the gravity. And then this is we can use I for x0 to 4 Ag in 0. Suppose we have inertial frame to describe the field of the gravity field, and that would be my notation sometimes. Okay, so F equal to mg in spatial algebra. This one is I times Ag. Okay, so that's the first one. So then, currently for backward propagation, you start from the lift. You start from the last body for which there's no additional children anymore. You compute, you find out uniquely the force at the joint. I'm going to ask maybe Liuben, what do you think? Here, suppose I got this F4, what is tau of 4? We need to know the joint torque, right? What is tau of 4?
Tau 4 equals to S4 transpose F4.
Okay, it's a projection of the wrench onto the screw axis. Okay, because the screw axis is only space for the motion. Okay, that's exactly correct. Okay, that's good. So then if we give another example, suppose we are working with 3 are the same as 4, let's working with body 2. Okay, for body 2, it's has 4 external forces, including the gravity. I would say this is a F2, that will be this guy, right? And equal to I2 A2 plus V2 cross I2 V2. That's the motion part. And also this is F2 is the force applied to body 2. And you know the force and the reaction force are the same. So the F3 is the force the body 2 prior to, this is my F3, right? If the body 2, the force applied from body 2 to onto body 3, then body 3 also apply a negative F3 force here, right? So here will be negative F3, but move to the right will be positive F3. Okay, positive F3 and positive F4, because that's the force body 2 apply to other, not the body 2 experience. So, and minus, this is Fg2. Okay, because G is something applied to the body. F3 and F4 is the force body to apply to the rest. This is the definition of the, it's clear for the direction of the force would be good. I think that's it, right? So for this part, we all know all of them. Suppose we move backward from the lift, then F3 already computed. We know F3, we know F4, and we know this is given. This is the gravity term, and this is the motion, and we already computed this from forward path, so we can compute F2 as well. So overall, we will have tau 2 equal to S2 transpose F2. Oh, sorry, S2 transpose F2. Okay. Hopefully you are familiar with this structure now. Now I'm going to ask you to see the structure of this force. The joint force, let's say 2. What does this force? What do you think the force is used? Okay, this force is used to provide motion, to generate motion of this, right? The force you apply for to some object, that something will move, have acceleration. Okay, that's first component is used to generate motion of body 2. And second component is used to counteract other kind of forces, right? So that's whatever other force you just add here. Okay, the positive sign means the body applied to the environment. Environment here is means 3. Okay, the negative sign is somehow other environment like gravity. If I push, let's say if I have a force here, let's say called F hat, then that will also be minus. Okay, minus on the right hand side means a force applied to the body, and the gravity is one particular force that we know and to apply to the body. Okay, so that's the rough structure. Let's write down the algorithm. I think the algorithm in Roy Featherstone, they have a complete algorithm. So let's say let's first initialize. Initialize, there's a trick, by the way. Let me think. Yeah, this is my body 0, suppose. Okay, it doesn't move, right? So its velocity is 0. It doesn't really move. It's fixed to the environment, inertia. Okay. But acceleration wise, oftentimes you have the trick. A0 equal to negative AG. Okay, because this part is hold on. This part is inertia of 2, let's say times x0 to 2 ag0. Okay, so you need to take care of all. Each link has this term. Okay, this term is it's because of the gravity. Gravity field is same. Okay, and we can think about the body, the 0 body. The environment has a downward acceleration, and that's take care of everything. You can ignore this term during the formulation. Of course, you don't have to do this, but this is typically a common trick that people use to simplify the code. Okay. Forward pass, let's just think with me, because we already teach you how to derive it. From link 1 or joint 1 to link n. Okay. Velocity wise, vi equals to let's say x pi, the parent velocity, change of coordinate, times V, V parent, depending on which is your parent. You only have one parent, by the way, okay? So the current velocity equal to previous parent velocity. Since we're doing local frame, then I need to change from parent's frame to my current frame plus the current joint. Okay, so it's the SI theta I dot. Okay, that will be my velocity. Then acceleration is x pi I acceleration of pi. Okay, when I didn't say pi here, that means expressed in the local frame, in that the parent local frame, plus SI theta I double dot plus some cross term vi. The S frame means S body. They are the same spatial velocity times SI theta I dot. Okay, that's the most important thing. Okay, and also in the forward path, we did a little bit about force to actually neutralize force for the backward path. So that's Fi equal to II plus Vi cross. That's the force cross. Okay, most force vector cross. II Vi. Okay, what does this mean? This part. Let me draw some box here. That's my forward path. Okay, let's erase this. Let's say this part is my forward path, and this guy means what? This I would say the range or force. Let's say range. Okay, range due to I's body motion only. Okay, so this force is not actual force. The force has different. Well, the force have different contribution to, so contribute to different things, right? The first one, force contribute to the motion of that link, particular link. The other thing is the force used to counteract other external forces. Okay, so so this part only consider the motion part. Okay, and then we need to backward somehow fix it. Okay, this is the forward path. Now we can do the backward. Backward is very easy. So for I equal to n back to, let's say, -1 to 1, right? Let's use MATLAB or Python's notation. At the beginning, I would say, first node, there's no, okay, the end or the leaf node, there's no children. The force or the joint torque, it's only used to generate motion. Suppose there's no external force, okay? Only used to generate motion. So at the beginning, tau I is just SI transpose Fi. Okay, this Fi is correct, right? But now, as you move backward, this Fi is not correct anymore. So you need to add the force. You need to add the additional force that you need to counteract. Okay, so for example, at this I know my parent I has to equal to my previous this one. So far, this guy, okay, before this line of code, this parent I is the parent I's force that contribute to only the motion without any other thing. Okay. Now I need to know, because I's torque is determined, this guy is determined, then I star parent I, so the parent I, change your coordinate Fi. Because Fi is from I's frame, but now I need to correct my parent's force, and this I need to change to that local frame, and the local change coordinate for force is xi parent I star. Okay, that may need you a few seconds to maybe a minute to know. After this iteration, all this force will become correct. Okay, so exactly like this. After the first pass, this guy is determined. That's my F2, but that's wrong, right? the new F2, the true F2 would equal to this guy. When you compute F3, you already modify that. Okay, you modify that by adding F3, but also you change coordinate to that factor. And when you modify F4, you also modify this term because F2, 2 is a parent of 4. Okay. So these two terms will be already considered. Okay, and also we this gravity term has been uniformly addressed through this part. Let me comment if you feel confused. And let's say without this gravity term, trick, let's call that trick. Without this trick, we should modify. Let's modify this, let's call it 1. We should modify 1 to, I'm not sure whether you can see that. That will be my Fi equal to II AI plus Vi cross II Vi, then minus, okay? You just need to consider this term explicitly now, okay, and not this term. So it's minus, that force is X0I AG0. Okay. Why not directly find AGI? That's how you compute it, right? Because AG0 you can immediately construct it. Then depending on your frame things, you can compute AGI by doing the change of coordinate for spatial acceleration. Okay. Any questions? Ruben, that's okay for you?
Yeah. Okay.
Forward pass, backward pass. You know exactly its link is nothing but the force balance and use Newton-Euler equation. Okay, there's nothing fancy. A few lines of code, very efficient. You can simulate. Okay, you can write your own recursive Newton-Euler algorithms. You can use that to generate forward dynamics. Maybe I will cover that maybe next time. But bottom line is that you can simulate almost every robot as long as you were given a tree, given a URDF file. You can do this recursively. Suppose all the inertial things are specified correctly. Okay. So that's the algorithm. I want to use algorithm to construct the overall analytical expression. Okay, I think modern robotics and also Marie's book also have that. But let's try to have some simple way to introduce this.